Hey guys, welcome back to another video and another series. In this series, we're going to solve a few hard questions from physical chemistry, that is from A2 level chemistry. And in this video specifically, we're going to solve a few hard questions from Equilibria, that is pH calculation and equilibrium constant calculation. So the first question I have from 2009 May-June session, and let's solve this one. That is saying 100 cm cube of an aqueous solution containing 0.5 grams of X was shaken with 20 cm cube of hexane. It was found that 0.5 grams of X was extracted into hexane. So initially you have 0.5 grams of X and in aqueous solution, that is in water. Now the moment 20 cm cube of hexane has been poured in, a certain amount of X has been extracted, and that amount turns out to be 0.4 grams, right? So they're telling you find the KPC. Very simple. What you're going to do is find how much has been extracted into, what concentration is of X is present in hexane and what concentration of X is present in H2O. So find those two out. You're going to basically do 0.4, that is grams of X in hexane, and in what volume? 20 cm cube. What is left in the water solution? 0.5 minus 0.4, that is going to be 0.1 grams of X is left. That is 0.1 divided by 100 cm cube. Now you may ask, why not turn it into moles? Well, for one thing, you don't know the MR of X. The second thing, the MR, if you divide the mass by MR, molar mass, the MR and MR gets cancelled off. So even if you can turn it into moles, you don't have to, you shouldn't. It's going to be a waste of time because the MR and MR gets cancelled off. So it doesn't really matter. Similarly, with CMQ, I don't need to turn it into DMQ because the divide by 1000 and divide by 1000 gets cancelled off. It doesn't really matter. So you don't need to turn CMQ into DMQ. You don't need to turn grams into DMQ. In this case, in KPC's case, not in other cases. Anyways, in this case, now notice one thing. Find out the KPC, that is ratio of what concentration of X in solvent hexane and in solvent water. Now, if you solve for the ratio, you're going to find the ratio is going to be 20. Now, a lot of people also have this confusion that what am I going to put in the numerator? What I usually do is whatever is mentioned first in the question, in this case hexane, I'm going to put that in the numerator, and whatever is mentioned later, that is in this case water, I'm going to put that into the denominator. And in some cases, if I know that this is going to dissolve more of the solvent, I'm going to easily just put it into the numerator because I'll get a value larger than 1. So you can go for that. You can also go for the sequence mentioned by the question. That is, I guess, a safer thing to do. But yeah, anyways, we know the KPC between solvent hexane and solvent water is actually 20 for solute X, for X. Fair enough. Now, second question, this is where the problem is. It's not a problem, it's fairly simple. But still, if two 10 cm cube portions of hexane were used instead of a single 20 cm cube portion, calculate the total amount of X extracted and compare this with the amount extracted using 1 cm cube of portion. Fair enough. Now listen carefully. They're telling you that in the case that you had 20 cm cube of hexane being put on top of the water solution, in that case you're extracting 0.4 grams of X. Now if I put in 10 cm cube of hexane separately on two different occasions, how much of X am I able to extract, right? So what you need to do is you need to calculate for 10 cm cube of hexane, how much of X has been extracted. Then again, with the leftover solution of water, again carry out the same extraction process by putting in 10 cm cube of hexane. In that case, again, see how much of X has been extracted. Now add both the amounts extracted up to see if it is more than previously calculated or less than. Compare this with the amount extracted in the previous question. Now, to carry this out, I'm going to consider the amount of hexane that has been extracted, amount of X that has been extracted to be X, right? So let's consider X grams of X has been extracted into hexane when there is 10 cm cube of hexane. And I can solve for this X since I know the KPC. KPC is 20 and I know X gram, I don't know, but X gram is going to be extracted by 10 cm cube of hexane. And you're going to be left with 0.5 minus X because X has been extracted. And in what volume? 100 cm cube. Now find X. This is going to be 0.3333 recurring, right? If you solve for X, that is. Now, this is the grams of X that has been extracted in the hexane solution. That is when you have 10 cm cube of hexane. So what is the amount, or mass of X left into the water solution? It is simply going to be 0.5 minus 0.33 recurring. And that turns out to be 0.166. 0.166 recurring. Fair enough. Now, you again need to carry out the same extraction process with another 10 cm cube of hexane. So again, I take 10 cm cube of hexane and I'm going to extract Y grams of compound X or solute X into the hexane volume, into the hexane solution. So I'm telling you, of the 0.166 grams of X left, of the 0.166 grams left into the water solution, I'm going to extract Y mass into the hexane solution. So I'm going to form this equation as 20, that is the KPC is equals to Y mass extracted into the 10 cm cube of hexane, and I'm going to be left with 0.1667 minus Y divided by 100 cm cube of water. Now see and solve for Y and see what is the amount of solute X being extracted in the new process. In the previous process, we saw 0.33 grams. And now when I solve for this, I'm going to get the Y to be 0.11 grams. Great. So now add both of those up. That is 0.33 in the previous case and 0.11 in the new case, and it's going to be 0.44. Hence, at the end of the day, you have extracted more of X by having two different trials, that is having two different separation process. The KPC is constant. The amount of X in water is also constant. However, what's changed is the number of trials, the number of execution, right? So I've separated it twice, right? Once 10 cm cube, then again 10 cm cube. And at the end of the day, I'm left with 0.44 grams into the hexane solution. Great. So that is your question 1, right? 0.04 grams more. Now, question 2, this is going to be from what? Winter 21 QP42. Great. Let's read this question. Ethoxyethane, that is this, can dissolve both in water and in octane 1-ol. The expression and numerical value for the partition coefficient of ethoxyethane between water and octane 1-ol are given. water and octanol are immiscible. The Kpc between this and this, that is octanol and water for ethoxyethane, is going to be 6.76 at 20 degrees. That is not going to matter. But anyways, so the Kpc between alcohol and water is going to be 6.76. Fair enough. Now, in an experiment, octanol at 20 degrees of Celsius is added to a solution of ethoxyethane at 20 degrees of Celsius. The mixture is analyzed immediately, and a value of Kpc is calculated. The calculation is performed correctly. The value calculated is 5.625. Great. And explain why the value calculated is less than 6.76. Now, this part of this question is important to follow because this is where they're literally answering the question. So they're telling you, why has the Kpc not reached its real value? So what has happened is there is a certain mass of ethoxyethane in water, right? Now, what has happened is the equilibrium has not been established, meaning all of the ethoxyethane could not travel to the alcohol solution. That is, that equilibrium has not been established. So all of the ethoxyethane could not travel to the alcohol part of the solution. So we need to give it more time for the equilibrium to be established. So I'm going to answer it as the equilibrium has not been reached since it is analyzed immediately, right? Immediately they're taking the reading, right? They're analyzing the solution. Great. Now all ethoxyethane could not travel to octanol. So the concentration in octanol is less. Now, since the concentration of octanol, that is ethoxyethane in octanol, is less, that is also why your Kpc value is less. Now for part B, it's fairly simple. A second experiment is performed and the value of Kpc is found to be 6.76. The concentration of ethoxyethane in octanol there is 7.62 grams per dm cube. Calculate the concentration in gram per dm cube of ethoxyethane in the aqueous layer. So they've given you the Kpc, they've given you the concentration in gram per dm cube of your octanol, that is alcohol, and the concentration in alcohol, and they are asking you to find the concentration of ethoxyethane in aqueous solution. Very simple. You have your Kpc given, and you have concentration of alcohol given, and you need to find out concentration in the aqueous solution. So just make X the subject over here, and you're going to get 1.127, that is 1.13. Fair enough. Now again, another tricky part is the part 2 over here. Notice they're telling you 100 cm cube of the octanol layer is taken and shaken with 100 cm cube of water. So they're taking the same solution of octanol as present over here. That is, over here, every 1 dm cube or 1000 cm cube of octanol layer has 7.62 grams of ethoxyethane. So they're telling you they're taking the same solution but 100 cm cube of it and mixing it up with 100 cm cube of water. Calculate the maximum amount in moles of ethoxyethane that can be extracted into the water in terms of mole. Fair enough. So I know that there is 7.62 grams of ethoxyethane in 1000 cm cube of octanol. So over here, every 1 dm cube, 7.62 grams of ethoxyethane. So for 100 cm cube, how much is it going to be? Just divide by 10, and it's going to be 0.762 in 100 cm cube, right? So divide by 10, and it's going to be 0.762 in 100 cm cube of octanol layer. Now, they're also telling you they're mixing it with 100 cm cube of water. Now, how much will it be extracted into the water layer? Use Kpc to find it out. So Kpc, 6.76. And initially the octanol layer has 0.762. Now some of it will be extracted into what? The water solution. So how much will be extracted? I am considering it to be X. So how much will be left in the octanol solution? 0.762 minus X grams. So now both are 100, so cancel it off. And at the end of the day, your X turns out to be 0.0982. That is grams, not moles. Keep that in mind. Now you have to turn it into moles as well. How do you turn it into moles? Now simply notice they've given you the molecular formula. So you have to find the molar mass. It's 12 into 2 plus 5 plus 16 plus 12, 12 into 2 plus 5. Find the molar mass and divide this by MR. Now when you do that, you're going to find the moles, and that turns out to be 0.0013. And that is going to be your answer, 0.0013. And that is going to be your question 2, right? This is the tricky part, and this is not exactly tricky, but somewhat, right? So yeah. And next, let's move on to question 3. Fair enough. Question 3. What are they saying? So part C of some question in March 19, paper 4.2 is telling you, at room temperature, N2O3 dissociates into NO and nitrogen dioxide. Write the expression for Kp, pressure constant, for this equilibrium. Include the units in your answer. Fair enough. So I have NO in gaseous form. I have NO2 in gaseous form as the products of the numerator, and your reactant in the denominator. So I have to write P, P, P every single time, right? Since all of these are gases. What is the unit going to be? This is going to have a unit of PA. This is going to have a unit of PA, PA, and PA. One cancels off, and you're left with 1 PA, so 1 Pascal. Fair enough, that is your unit. Moving on, 1 dm cube of flask at 25 degrees Celsius is filled with pure N2O3 at an initial pressure of 0.6 atmospheric pressure. At equilibrium, the partial pressure of NO2 is 0.48 atmospheric pressure. Calculate the partial pressure of NO and N2O3 at equilibrium. Hence, calculate the value of Kp at 25 degrees Celsius. The pressure is proportional to the concentration, and which is again proportional to the moles. How, you ask? Because notice one thing. In general that 24 dm cube is going to be 1 mole of gas, right? 1 mole of gas occupies how much space? 24 dm cube. Now, the moment you add pressure, right? The concentration increases. Because the volume decreases. Concentration is going to increase, right? So, within the same volume now, you're going to occupy greater amount of moles, right? So, as pressure increases, so does concentration, and as concentration increases within the same volume, you're going to have greater amount of moles. So, using this ratio, I can find, what are they asking me to find? I can find the partial pressure, right? So, initially, you had 0.6 atmospheric pressure, 0.6 atmospheric pressure of N2O3, that is before the reaction is taking place. And after the reaction is taking place, notice, you're left with 0.48 and 0.48 according to your partial pressure of NO2. So initially, they're starting off with 0.6 atmospheric pressure of N2O3. Now, the moment equilibrium has been reached, they're telling you 0.48 atmospheric pressure is the pressure of NO2. So they've given you NO2. So NO2 partial pressure is going to be 0.48, right? Fair enough. Now, also consider this. Notice your moles are proportional to pressure. Okay? Your moles are proportional to what? Pressure. So, notice the ratio of moles. 1:1:1. Agreed? Fair enough. So, if there is 0.48 moles of NO2, what is the moles of NO going to be? I mean, in terms of partial pressure, sorry. what is the partial pressure of NO going to be? It is going to be 0.48 as well, because the molar ratio is same. Molar ratio is same. Hence, the partial pressure by both of these compounds is going to be the same as well. 0.48. 0.48. Fair enough. Now, after as taking place, you're going to see that the rest of N2O3 is going to be 0.12, since 0.6 minus 0.48. Now you're going to ask, how is there 0.12 left? Very simple. Since if one mole of N2O3 dissociates, dissociates, it's going to produce 2 moles of gases. That is one NO and the other NO2. So if 0.48 of it dissociates, right? If 0.48 dissociates, it's going to create 0.48 of NO, and it's also going to create 0.48 of NO2. So you're ultimately left with 0.6 minus 0.48 partial pressures, right? So you're going to be left with 0.12 partial pressure, right? At equilibrium. Now, to find the Kp, use the partial pressure to find the Kp. That is going to be 0.48 whole square, that is your product partial pressure, divided by 0.12. And ultimately, you're going to get 1.92 as your answer. And your Kp is going to be 1.92. And that is going to be your question 3. Fair enough. Now, for question 4, it is from your winter 19 paper 4.1. And this question is saying, bromic acid, HOBr, is a weak acid. Its dissociation constant is 2 into 10 to the power minus 9 mole per dm cube. Calculate the pH of 0.2. Now, they just have the weak acid, which is going to dissociate and form H plus and your OBr minus, right? So it's going to dissociate and form a bunch of H plus concentration, which is going to be used to find the pH. So simply, they've given you the Ka, and you know the concentration of the acid, and you don't know the concentration of either OBr minus and H plus. So you're going to consider over here, since there's only HOBr present, right? It is going to dissociate and then form H plus and OBr. I can consider the concentration of H plus and OBr minus to be the same. So I'm going to consider that as H plus squared, because both of them are going to be in same concentration. Because when 1 mole is going to dissociate, it's going to also form 1 mole of H and 1 mole of OBr minus, right? Great. So I'm going to consider H plus square and now make H plus the subject. So I have 2 into 10 to the power minus 9 times concentration of HOBr, that is 0.2. And I'm also going to now make H plus the subject by taking a square root on this side. So my H plus concentration is 2 into 10 to the power minus 5. And your pH is going to be minus log of that, and that is 4.7. So fairly acidic. Now next up, 5 cm cube of 0.2 mole per dm cube potassium hydroxide are added to 20 cm cube of 0.2 mole per dm cube of HOBr acid. Calculate the pH of the buffer solution produced. Fair enough. Now what's going to happen over here is, first, you have the potassium hydroxide acting as a base. That is going to react with your HOBr. So at the beginning, acid plus base reaction will take place where a salt is going to be formed. And you're going to have H2O. So over here, let's first go through the reaction, right? KOH, what mole of KOH is present? Potassium hydroxide, that is going to be 0.2, that is 0.2 mole per dm cube times the volume, 0.005 dm cube, and that is going to be 0.001 mole. For HOBr, you have 0.02 volume dm cube and 0.2 mole per dm cube of HOBr. Now, when you find the moles, it's going to be 0.004 moles. Fair enough. Now, if I now write down the equation, it's going to be a ratio of 1:1. So 1 KOH reacts with 1 HOBr to form 1 KOBr salt and 1 molecule of water. Now, since the ratio is 1:1:1, I can say that this is the limiting reagent. KOH, potassium hydroxide, is the limiting reagent. And it is going to react with this and form 0.001 of KOBr salt. How much salt? 1 0.001 mole of KOBr salt. Fair enough. So now there is going to be some amount of left HOBr. How much you ask? 0.003. Because 0.001 reacted, but the rest is left. Now what's going to happen is now you're going to figure out what concentration of HOBr is left. Because I know 0.001 mole of salt is left in the solution, in the equilibrium. But I also have 0.003 moles of acid left. So very simply, you know, since it's a weak acid, it is also going to dissociate. So I'm going to use that to find out the pH. So I'm going to first find out the concentration, that is 0.003 mole per what dm cube? 25 dm cube. 25 into 10 to the power minus 3 dm cube. Now why this? Because notice, you're adding 5 cm cube to 20 cm cube. So the total volume is going to be 25 cm cube, or rather 25 into 10 to the power minus 3 dm cube. This is your concentration of HOBr that is going to go into the denominator, and in the numerator you have to find out the concentration of H+. How much H+ is going to dissociate in the solution, in the equilibrium solution. And you also have the concentration of salt. How you ask? Because over here, you already produced the salt. This OBr minus is your salt. And this you already have produced in what amount? 0.001 moles. We use that. 0.001 moles divided by the total volume of solution, that is 25 cm cube. Now, you also know the dissociation constant, that is 2 into 10 to the power minus 9. Now you're going to find out the H+ concentration if you make it the subject, and that is going to be 6 into 10 to the power minus 9. Now plug it in into the minus log formula, and you're going to get a pH of 8.22. Meaning, this is not an acidic solution. This is actually a basic solution, because the HOBr is unable to dissociate as much. Due to the presence of this base, OBr minus, the HOBr is unable to dissociate as much H+ ion. Hence, your concentration of H+ is less, hence your pH is also high, right? It is basic in nature. Okay, now question 5. This is going to be from summer 13 paper 4.2 and some question part B. And this is saying, a buffer solution is to be made using 1 mole per dm cube of ethanoic acid and 1 mole per dm cube of sodium ethanoate. So you're taking same concentration of both salt and acid. And now they're asking you calculate to the nearest cm cube the volumes of each solution that would be required to make 100 cm cube of a buffer solution with pH 5.5. Okay. So now, when you have 1 mole per dm cube of acid and 1 mole per dm cube of salt, they're asking you what volume of each should I take to ultimately make 100 cm cube of a buffer solution with a pH 5.5. Now, how do I find what the volume of either is going to be to finally add up to 100 cm cube and also have a pH of 5.5? That I need to figure out. And they've also given you the dissociation constant of the acid. So I know I have to work with the equilibrium constant, right? Ka, I mean the dissociation constant. Now, how do I get to there? How do I get to knowing the concentration, equilibrium concentration of acid and salt? First, I need to find out what the volume of either acid, either salt is going to be, right? So I need to find out the concentration of both salt and acid. Now, before that, I need to find the volume to understand what volume of either I'm going to take, of 1 mole per dm cube of acid and 1 mole per dm cube of salt. Mind you, whatever volume I take, this should add up to 100 cm cube, such that if I take 20 cm cube of acid, I'm going to take 80 cm cube of salt solution. such that it adds up to 100 cm cube. Great. Now, granted both are 1 mole per dm cube, let us consider the the volume of acid to be x centimeter cube. I'm going to consider the volume of acid to be x centimeter cube since I don't know how much it's going to be. That's what we're going to figure out. So, considering the volume of acid to be x centimeter cube, ultimately your volume for salt solution is going to be 100 minus x, because whatever the volume of acid is, the rest is going to be your salt solution. So 100 minus x. Great. Now, you have to find the moles of the ethanoic acid. How do you find the moles? Concentration times volume. Concentration you know to be 1. Volume you know to be x. But in cm cube, so turn it into dm cube by dividing by 1000. Done. Next, moles of ethanoid ion. How do you find the moles? You know concentration to be 1. And what is the volume? 100 minus x. Turn it into dm cube, divide by 1000, and this is going to be your moles of ethanoid ion. Now what? Now find a new concentration in equilibrium. Mind you, whatever you figured out over here to be your moles or to be your volume, all of these are with respect to 1 mole per dm cube of acid and 1 mole per dm cube of salt. However, after you take, let's say, x centimeter cube of acid and 100 minus x centimeter cube of salt, finally when they make 100 cm cube, the concentration of either is going to change. It is going to change from 1 mole per dm cube to a new value. Since you're adding other reagents, to the acid you're adding salt, and to the salt you're adding acid, so the volume is changing, right? The volume is changing for either the salt and acid. Hence, your concentration will also change. So, the new concentration, if I have to find out, how will I do that? For ethanoic acid, mole by volume. What is the mole? The mole is this, x by 1000, x by 1000. What is the volume? 100 cm cube, divide by what? 1000. Why? Because turning into dm cube, right? So mole per dm cube, your concentration. This turns out to be x by 100. Now, of the sodium ethanoid ion, similar thing. What is the mole? This is your mole. What is the volume? 100 by 1000, turning it into dm cube. What is your concentration now? Finally, after you cancel everything off, 100 minus x divided by 100. So now, you have the concentration of acid, you have the concentration of ethanoid ion. Now for the Ka, you need a couple of things. H plus, salt, acid. These are all the variables you need to know the concentration of. Ka, I know. Salt, I know. Acid, I know. These two I just figured out. Ka, they have already given you. pH, let's find out. Sorry, I mean the H plus concentration. Let's find the H plus concentration. They've given you the pH, so reverse operation and find the H plus concentration. I know minus log of H plus concentration is 5.5. So now 10 to the power of minus 5.5 is going to give me this concentration of H plus. That is 3.16 into 10 to the power of minus 6 mole per dm cube. This is your concentration of acid. So great. Now you know the dissociation constant, you know H plus concentration, you know the concentration of salt, you know the concentration of acid. Everything you know. So what are you going to find? You're going to find the volume, X. Remember, initially we considered X to be the volume of acid, right? So our ultimate job is to find out what volume we're taking. So I'm going to make X the subject and find for X. And this X turns out to be 15 cm cube. And 100 minus 15 is going to give you the salt volume. That is going to be 85. So ultimately, this is your answer. Volume of ethanoic acid and volume of the salt solution. Right? Fair enough. So this is how you solve this atrocity of a question. It is quite complicated. In general, Equilibria does have a few difficult questions every once in a while, but this was quite the outstanding question. Anyways, so moving on to the next part. These are not hard, but I'll still solve. Write an equation to show the reaction of this buffer solution with each of the following. Now, what's going to happen if you add HCl to the buffer solution? The salt is going to react with HCl because this is part base. So it is going to form the acid once again. The H plus is going to displace the Na, and Na forms NaCl, right? And when you add NaOH or increase the concentration OH, the acid reacts, forming your salt solution, that is sodium ethanoate and water, right? Fair enough. So this is how your buffer solutions equation is going to be. And lastly, choose one reaction in organic chemistry that is catalyzed by an acid and write the structural formula of the reactants and products in the boxes. This is of organic chemistry, but there are multiple examples of acid acting as catalyst. There are hydrolysis reactions, breaking down esters, breaking down polyamides and all that. So benzene reacting with HNO3, I've taken the example as, and that forms nitration. So after nitration, it's going to displace one H plus, forming benzene attached to a nitro group, forming nitrobenzene, right? And water. So that is your question 5, and that is going to be it for this video, and see you in the next one.